All right, diving into a really fascinating area today, and that is large language models.
LLMs, yep.
LLMs, exactly. These are getting so much attention for, well, obvious reasons, right? Generating text, reasoning, decision making. I mean, the potential here seems really huge.
Yeah, it really does feel like we're on the cusp of something big here.
And that's why we're doing this deep dive. We want to get past the hype and really look at this academically. What's really going on under the hood of these LLMs?
Yeah, the goal here is to provide a much deeper, more rigorous understanding, something that goes beyond the surface level explanations you often hear.
Exactly. And to do that, we're basing this deep dive on the paper, an overview of large language models for statisticians. Bit of a mouthful, but it's got some great insights.
It really does lay out the course concepts in a very structured way. Perfect for our deep dive here.
Perfect. So whether you're hearing about LLMs for the first time, or maybe you've got some basic knowledge but are looking for a kind of a more organized and deeper dive, well, you're in the right place.
We're going to be covering a lot of ground, but the aim is to be clear, easy to follow, and not get bogged down in, too much technical jargon.
Exactly. We're aiming for clarity. So over the course of this deep dive, we'll be exploring the fundamental principles behind LLMs, their intricate architectures, the training processes involved, and then we'll get into some important considerations about their trustworthiness and the potential they hold for statistical analysis.
It's a pretty exciting roadmap. Let's jump right in.
Yeah, let's do it. So starting at the very beginning, what is the core concept behind a language model? What are we even talking about here?
So, at the heart of it, a language model is all about predicting probabilities.
Probabilities. Okay.
Yeah, probabilities. Specifically, the probability of what word is going to come next in a sequence. So you give it a bunch of words, and the model's job is to figure out, okay, based on what I've seen so far, what's the most likely word that's going to follow?
Hmm. It sounds deceptively simple when you put it like that, but I mean, we're seeing these models do some pretty complex things. How does just predicting the next word lead to that?
Right, that's the key. You see, when you train these models on absolutely massive amounts of data, and I mean massive, they start to pick up on incredibly subtle patterns. It's not just about individual words anymore. They're learning syntax, semantics, even a bit of logic, all from those vast amounts of text.
So it's the scale of the data that really unlocks that potential.
Absolutely. And on top of the massive data, you've got these sophisticated fine-tuning methods that allow us to take these already impressive models and get them to follow specific instructions. Think about it. You can tell a model, hey, summarize this article for me, or translate this sentence into Spanish, and they can do it. It's pretty remarkable.
It really is. And I think it's important to remember that this didn't just happen overnight. There's been a whole evolution leading up to these powerful LLMs.
Definitely a fascinating history. We can trace the lineage back to early neural language models, or NLMs for short. Back then, the big innovation was using neural networks to represent words as vectors, a bunch of numbers that capture something about the meaning of the word.
So moving away from just counting how many times a word appears to, like, understanding its relationship to other words.
Exactly. Those vectors place words in a kind of semantic space where their position relative to other words reflects their meaning in relationship to each other. It was a huge leap forward.
A real game changer. And then what came after these NLMs?
Well, the next big thing was recurrent neural networks, or RNNs. They were specifically designed to handle sequential data, like text. You feed it one word at a time, and the network maintains a sort of memory of the preceding words, allowing it to capture dependencies in the sequence.
So it's like the network is reading the text word by word and trying to understand how each word relates to what came before it.
Precisely. But there was a snag. RNNs struggled when you threw really long sequences at them. The signal from earlier words could fade away as the network processed more and more words, making it hard for them to learn those long-range dependencies.
Kind of like trying to remember the beginning of a really long story after you've gotten to the end. All those details get a bit fuzzy.
Yeah, exactly like that. And this problem, it's called the vanishing gradient problem. It was a major hurdle.
It sounds like a real roadblock. So how do they get past that?
Well, researchers came up with some clever solutions. New types of RNNs were developed, like long short-term memory networks, or LSTMs, and gated recurrent unit, or GRUs. They basically introduced mechanisms to control the flow of information within the network, making it easier for them to hold on to those crucial long-range dependencies.
So they could remember the beginning of the story even after reaching the end.
Exactly. That was a big step forward. But then came a truly transformative innovation, the attention mechanism.
This is where things start to get really interesting.
Yeah, attention was a game changer. It basically allowed the network to focus on specific parts of the input sequence, even parts, when processing each output. It's like the model is selectively paying attention to the most relevant pieces of information for whatever it's trying to do.
So instead of just taking in the whole sequence in order, it can jump around and focus on the most important parts. Sounds incredibly powerful.
It is, and this led to the architecture that dominates most of modern LLM in today, the transformer.
Ah, the transformer. I feel like I've heard that name everywhere.
And for good reason, the transformer did away with the recurrent processing of RNNs entirely, and instead relied solely on this attention mechanism, along with some other key components we'll talk about in a bit.
I'm eager to hear about those. But first, since the transformer came on the scene, we've seen explosion in LLM capabilities. What's driving that rapid progress?
Well, a big part of it is scaling. By scaling, I mean increasing the number of parameters in the model, essentially its capacity to learn, and also the sheer amount of data we're training them on. We've seen that bigger models trained on more data just keep getting better.
So it's a brute force approach in a way. Just make things bigger and feed them more information.
It might seem like that, but there's a lot of finesse involved in how we design and train these models. And of course, there's a limit to how much we can scale. Computational resources are finite, and there's the whole issue of sustainability to consider.
Right, training these massive models consumes a lot of energy. And the paper mentions all these different LLM families now, Llama, Mistral, GPT, Claude, DeepSeek. It can be a bit overwhelming to keep track of.
It can be. These are all significant players in the LLM landscape, and each has its own strengths and weaknesses. Some are open source, some are proprietary, they vary in size and the kind of tasks they excel at. And importantly, they also have different hosting requirements. Some can run on a standard laptop, while others need massive server clusters or are only accessible through cloud-based APIs.
It's a whole ecosystem evolving at an incredible pace. Okay, so we've covered the fundamentals and the historical evolution. Let's dive into the architecture itself. You mentioned the transformer being key. What are the main building blocks of this architecture?
All right, so we've gone from models that process text sequentially to the transformer, which, as I mentioned, relies heavily on this attention mechanism to process the whole input sequence in parallel. A core concept here is pre-trained language models, or PTMs for short. These PTMs take self-supervised learning techniques and combine them with the transformer architecture.
Self-supervised learning. That means the model learns without explicit labels, right?
Exactly. The model basically learns by trying to predict masked or missing words within the text itself. It's like giving the model a puzzle and asking it to fill in the blanks.
So it's learning the structure of language by figuring out how words relate to each other without us needing to tell it explicitly.
Precisely. And the transformer architecture, with its self-attention mechanisms, is perfectly suited for this. It allows the model to capture both short-range and long-range dependencies within that unlabeled data. It's quite elegant, really.
It sounds it. Now let's get into the nitty-gritty of the transformer. You've talked about this attention mechanism. Can you break down how it works at a more detailed level?
Sure. So imagine the model is generating a sentence, one word at a time. At each step, the attention mechanism allows it to look back at all the words in the input sequence and essentially decide which words are most relevant to the current word it's trying to generate.
So it's not just considering the words immediately before it, it's taking into account the whole input sequence.
Right. It's like if you were writing a story and you were about to write the next sentence, you might think back to earlier parts of the story that are relevant to what you're about to write.
I see. It's like the model is dynamically focusing its attention on the most important parts of the text.
Exactly. And mathematically, this involves calculating a similarity score between a query, which represents the current word being generated, and each key in the input sequence. These scores are used to compute weights, which are then applied to the corresponding values from the input. The result is a weighted sum of these values representing the attended information.
Okay, that's a bit technical, but I think I get the general idea. It's a way for the model to prioritize information from the input based on what it's currently trying to generate.
Exactly. Now, the transformer itself is built around this attention mechanism. It follows a sequence-to-sequence structure, meaning it takes an input sequence and produces an output sequence. It consists of two main parts, an encoder and a decoder, each composed of multiple identical blocks stacked on top of each other.
What are the roles of the encoder and the decoder?
So the encoder takes the input sequence and transforms it into a sequence of continuous representations. Think of it as trying to understand the meaning of the input and encoding that meaning into a numerical form that the decoder can work with.
And the decoder then uses those encoder representations to generate the output sequence.
Exactly. It takes those representations and, usually one word at a time, generates the output sequence, taking into account both the encoded input and the words it's already generated.
Like a translator working from a source text.
That's a good analogy. Now, each of those encoder and decoder blocks, they have some key components. The main ones are a multi-head attention module, or NHA, and a position-wise feed-forward network, or FFN. These modules are surrounded by residual connections and followed by layer normalization, which helps with training stability.
So a lot of clever techniques packed into each of those blocks. You mentioned multi-head attention. What's the multi-head part all about?
That's a really clever idea. Basically, instead of doing the attention calculation just once, the multi-head attention module does it multiple times in parallel, each time using slightly differently learned parameters. This allows the model to attend to different aspects of the input simultaneously.
So it's like having multiple experts, each focusing on a different part of the text, and then combining their insights.
That's a great way to put it. It allows the model to capture a much richer understanding of the relationships between words in the text. Now, the decoder blocks are very similar to the encoder blocks, but they have one extra piece, a cross-attention module. This lets the decoder attend to the output of the encoder, effectively bridging the input and output.
So it's like the decoder's checking in with the encoder to make sure it's on the right track as it's generating the output.
Exactly. And another important detail is that the self-attention in the decoder is masked. This means it can only attend to words that have already been generated, not future words. This ensures that the generation process is autoregressive, meaning each word is generated based on the preceding words.
That makes sense for generating text sequentially. Now, you also mentioned positional encodings. Why are those necessary in the transformer architecture?
Good question. RNNs naturally process text in order, but the transformer treats all the words in the input sequence simultaneously, so it needs a way to know the order of the words. Positional encodings provide that information.
So it's like telling the model, hey, this word is the first word, this one's the second, and so on.
Exactly. The original transformer used sinusoidal functions to create these positional encodings. There are more advanced methods now, like rotary positional embeddings or ROPE, and contextual positional encodings, or CoPE. They all aim to provide the model with a sense of word order.
So different strategies for the same goal. Okay, back to multi-head attention. What's the benefit of having those multiple heads?
So the core of the attention calculation is something called the scale dot product attention. It's a way to measure similarity between the query and the keys we talked about earlier. Now, multi-head attention does this calculation multiple times in parallel, each time using different learned parameters. This allows the model to attend to different aspects of the input at the same time.
So it's like looking at the text from different perspectives, capturing different types of relationships between words.
Exactly. And these different perspectives, or heads, are then combined to produce the final output of the multi-head attention module. It's a very powerful mechanism for understanding the nuances of language.
It makes the model more sophisticated in a way. The paper also mentions decoder-only transformers. What are those and why are they so popular for LLMs?
So, as the name suggests, decoder-only transformers ditch the encoder part and just use the decoder. They're mostly used for generation tasks, where the goal is to predict the next token in a sequence, given the preceding tokens. Language modeling, the task we talked about earlier, is a prime example.
So focused on generating text, not necessarily on understanding or analyzing existing text.
Right. And a really important development in this area is instruction tuning. By fine-tuning these decoder-only models on a variety of tasks, all framed as instructions, we can get them to generalize to new tasks much better.
So you're teaching the model to understand and follow instructions rather than just learning specific tasks.
Exactly. And this has led to some incredibly impressive results. Models like GPT, Alama, and Mistral, they're all based on this decoder-only architecture with instruction tuning.
That's a really insightful overview of the transformer architecture. It's quite a marvel of engineering. Now, how do we go about evaluating these complex models, especially given their ability to generate open-ended text? Traditional metrics don't seem like they'd cut it.
That's a great point. Evaluating generative models is tricky. We can't just rely on exact matches to some predefined answers because these models are designed to be creative and generate novel text. We need more sophisticated evaluation methods.
So how do we judge their performance?
Well, there are a few approaches. One interesting one is Chat.Arena. It's basically a platform where you can pit two LLMs against each other in a kind of battle of the bots.
So like a competition to see which model performs better.
Exactly. And the judging is done by humans. They see the outputs from the two models without knowing which is which, and they vote on which one they think is better.
Kind of like a blind taste test.
Yeah, exactly like that. And they use this clever system called the ELO rating system to keep track of the model scores based on these votes. It's a system borrowed from chess, actually, where it's used to rank players.
That's really clever. It leverages human judgment to to evaluate these complex systems. So we've covered the fundamentals, the architecture, and even evaluation. Let's move on to the training process itself. It sounds like it's a multi-stage affair.
It is. There's a lot involved in training these LLMs, and the paper outlines a few key stages. The first, and perhaps most important, is pre-training. Back around 2017, 2018, 2019, there was a fundamental shift in how we train these NLP models. We moved away from pure supervised learning, where you need lots of labeled data, to this two-phase approach. Pre-training by fine-tuning.
So you first train the model on a massive amount of data just to give it a general understanding of language, and then you fine-tune it on specific tasks.
Exactly. During pre-training, we take the model, usually a transformer, and we train it on a huge corpus of text, just raw text without any specific labels or annotations. And the model learns to predict parts of the input itself, like masked words or the next word in a sentence. This is called self-supervised learning.
So it's learning by trying to fill in the blanks in a way. It's like a giant game of Mad Libs.
Kind of, yeah. And this pre-training stage produces a model, a really good grasp of language in general. It can then be fine-tuned for specific tasks by training it on labeled data for those tasks.
I see. So the pre-training is like building a strong foundation, and the fine-tuning is like specializing in a particular area.
Exactly. And there are several advantages to this pre-training approach. First, it lets the model learn really rich language representations that can be used for a wide variety of tasks. Second, it gives us a much better starting point for fine-tuning. Third, it can help prevent overfitting, which is when the model becomes too specialized to the training data and doesn't generalize well to new data.
The pre-training is a win-win. Now, what are the typical learning objectives during this pre-training phase? What's the model actually trying to predict?
The most common objective is standard language modeling. The model is trying to predict the next word in a sequence given all the previous words. It's like trying to guess what someone is going to say next based on what they've already said.
It sounds simple, but at the scale these models are trained on, it's anything but.
Exactly. And there are other self-supervised objectives as well, like corrupted text reconstruction, where the model tries to restore missing parts of a sentence, and full text reconstruction, where it tries to generate an entire text from some compressed representation. And these can be combined with auxiliary objectives like predicting the next sentence or the order of sentences in a document. All of these help the model develop a deeper understanding of language.
It's like giving the model a variety of language puzzles to solve, each one helping it learn something new.
Precisely. Now, all of this requires a ton of data. Where do we get all this text to train these models?
That's what I was wondering. I mean, we're talking about massive data set.
Right. There are two main categories of training data, general corpora and domain-specific corpora. General corpora are these huge collections of text from a variety of sources, web pages, books, scientific articles, code repositories, social media posts, you name it.
Wow, that's a lot of different types of text.
It is. Each source has its own pros and cons. Web pages offer a ton of data, but are often messy and need a lot of cleaning. Books are generally higher quality, but might be limited in their coverage. Academic papers are very specialized, and so on.
It's like creating a balanced diet for the model.
Yeah, a very diverse diet. And then there are domain-specific corpora, which are more focused data sets tailored to particular fields like finance, medicine, or law. They're used to fine-tune models for those specific domains.
So you start with a broad understanding of language from the general corpora, and then you specialize it with the domain-specific corpora.
Exactly. And deciding which data to use and how to mix different sources is a whole research area in itself. There are techniques for selecting the most relevant data and weighting different sources appropriately.
It sounds like there's a lot of art involved as well as science.
There is. Now, all of this training, it's incredibly computationally intensive. And this brings us to the concept of scaling laws.
Right, I've heard about these. It has something to do with the relationship between model size, data size, and performance, right?
Exactly. As we've been making these models bigger and bigger, researchers have started to notice some interesting patterns. What they've found is that, generally speaking, increasing the model size tends to lead to bigger performance gains than proportionally increasing the amount of data.
So bigger models are better, up to a point at least.
Well, it's not quite that simple. There are trade-offs. Bigger models are more expensive to train, both in terms of computational resources and energy consumption. And there's also the issue of diminishing returns. At some point, making the model bigger might not lead to much improvement anymore.
So it's about finding the right balance.
Exactly. And there's a lot of ongoing research into how to train these models more efficiently, how to get more out of the data we have. It's a very active area.
Fascinating. So we've got this model pre-trained on a massive amount of data. It has this broad understanding of language. Now, how do we get it to perform specific tasks effectively? How do we tell it what to do?
That's where prompting and fine-tuning techniques come into play. For these really large language models, the primary way we interact with them is through prompting. Instead of explicitly training them on specific tasks, we give them a prompt, which is like a set of instructions or a starting point, and they generate text based on that prompt.
So it's like giving the model a cue and it improvises from there.
Exactly. And the art of crafting these prompts is a whole area of research called prompt engineering. There are different types of prompts. You have hard prompts, which are just natural language instructions, and you have soft prompts, which are more like embeddings that are prepended to the input. And there are hybrid approaches that combine the two.
So it's about figuring out the best way to communicate with the model to guide it toward the desired output.
Precisely. And one really interesting thing about these LLMs is their ability to do in-context learning. This means they can learn new tasks simply by seeing a few examples in the prompt itself without any explicit fine-tuning.
So you're showing the model a few examples of what you want it to do, and it figures out how to generalize from those examples.
Exactly. It's like teaching a kid by showing them how to do something a few times and then they pick it up.
That's pretty amazing. But are there any limitations to this in-context learning?
Well, it can be sensitive to the specific examples you choose and the order you present them in. Researchers are working on ways to make it more robust, but it's still an area of active research.
Makes sense. Now, what about when we do want to fine-tune the model for a specific task? Is that still necessary?
It can be. Even though in-context learning is powerful, supervised fine-tuning, where we train the model on labeled data for the specific task, can still lead to significant performance gains, especially for tasks that require very precise outputs or where we have a lot of labeled data available.
So it's like taking that broadly knowledgeable model and giving it some specialized training.
Exactly. And one particular type of fine-tuning that's become really important is instruction tuning. Here, the idea is to train the model on a wide variety of tasks, all framed as instructions. This helps the model learn to understand and follow instructions in general, which makes it much more adaptable to new tasks.
So it's like teaching the model to be a good student, to learn how to learn.
That's a good way to put it. All of this is great for getting the model to generate text that's grammatically correct and factually accurate, but how do we ensure that the text is also aligned with human values that are helpful and harmless?
That's a crucial question. We don't want these powerful models to be used for malicious purposes.
Exactly. And this is where alignment techniques come in. One of the most important ones is reinforcement learning from human feedback, or RLHF for short.
I've heard about that. It involves getting humans to provide feedback on the model's outputs, right?
It does. It's a multi-stage process. First, we fine-tune the model on a dataset of human demonstrations of good behavior, like following instructions in a helpful and harmless way. This gives us a starting point for alignment.
So we're showing the model what good behavior looks like.
Right. Then we use the model to generate multiple candidate responses to various prompts, and we have humans evaluate these responses, telling us which ones they prefer based on criteria like helpfulness, harmlessness, and so on. This data is used to train a separate reward model, which can predict how humans would rate different responses.
So we're teaching a model to judge other models based on human preferences.
Precisely. And finally, we use this reward model to fine-tune the original language model using reinforcement learning. The idea is to maximize the reward signal from the reward model so the language model learns to generate text that humans would find more desirable.
It's like training a dog with treats. You reward the model for good behavior.
Yeah, that's a good analogy. And there are different algorithms for doing this reinforcement learning, like proximal policy optimization or PPO.
So it's a pretty complex process, but it seems essential for aligning these models with human values.
It is, and there are other alignment techniques as well. The paper mentions direct preference optimization, or DPO, which is a more direct approach that doesn't involve training a separate reward model.
What are the pros and cons of DPO compared to RLHF?
Well, DPO can be simpler to implement and often leads to more stable, but it can also be more prone to overfitting and might sometimes lead to less desirable responses if the initial model isn't good enough. It's an active area of research, and there are ongoing efforts to improve both RLHF and DPO.
It's good to know that researchers are constantly working on these alignment challenges. The paper also discusses the use of synthetic data for alignment. Why is that becoming increasingly important?
Well, as you can imagine, getting humans to provide feedback on all these different outputs is expensive and time-consuming. So there's a lot of interest in using AI itself to generate training data for alignment.
So using AI to align AI.
Exactly. There are different approaches. For example, we can use the language model to generate its own instructions or to evaluate its own outputs. This can be combined with human feedback to create a more efficient and scalable alignment process.
It's like having the model teach itself with some guidance from humans.
Yeah, that's a good way to think about it. But there are challenges with this approach too. We need to be careful that the model isn't just learning to game the evaluation system, that it's truly aligning with human values.
That's a valid concern. It's like teaching a student to pass a test without actually understanding the material.
Precisely. And that brings us to a really crucial aspect of LLMs, trustworthiness. The paper dives into several areas where statistical methods can help ensure that these models are reliable, unbiased, and safe to use. Let's start with uncertainty quantification.
All right, uncertainty quantification. Why is that so important for real-world applications of LLM?
Well, as impressive as these models are, they can sometimes generate outputs that are just plain wrong. They can hallucinate, making up facts or spouting nonsense.
Which can be quite dangerous depending on the application.
Exactly. So it's essential that we have a way to quantify how certain the model is about its outputs. We want the model to be able to say, I'm pretty sure this is correct, or I'm not so sure about this one.
So it's like providing a confidence score alongside the generated text.
Exactly. This helps users understand how much to trust the model's output, which is especially important in high-stakes situations.
Makes sense. But how do you actually measure uncertainty in something as complex as language generation?
That's a good question. There are different approaches. One is to use classic information theoretic measures like entropy, which can be calculated from the probability distribution over the next token. But researchers are also developing more sophisticated methods that take into account things like the semantic meaning of the generated text, the importance of different words in the output, and even internal signals from the model itself.
So looking at both the model's internal confidence and the consistency of its outputs.
Right. And one statistically rigorous approach is conformal prediction, or CP. It's a way to construct prediction sets with a guaranteed coverage probability, meaning we can say with a certain level of confidence that the true output will fall within that set.
So it's like providing a range of possible answers along with a measure of how likely each one is.
Precisely. And this can be really valuable in applications where we need to be extra careful about the model's outputs.
Absolutely. Now, another aspect of trustworthiness mentioned in the paper is watermarking. What's that all about?
So imagine you have an LLM generating text. How can you tell if that text was actually generated by the model or if it was written by a human? Watermarking is a way to embed a kind of hidden signal in the generated text that can be used to prove its origin.
It's like putting a secret mark on something to identify it later.
Exactly, and it's done in a way that doesn't affect the readability or quality of the text. There are different types of watermarks. Some are statistically based, using some biases in the word choice to encode the watermark. Others are more cryptographically based, using techniques like digital signatures.
So it's a way that ensures accountability to be able to trace the text back to its source.
Precisely, and this is becoming increasingly important as these LLMs become more powerful and widespread. We need to be able to distinguish between human-generated and AI-generated text, especially in situations where authenticity matters.
Definitely. Now, another big concern with these models is privacy. They're trained on massive amounts of data, often scraped from the internet. What are the risks here?
That's a crucial concern. There's a risk that these models could memorize sensitive information from the training data and then leak that information in their outputs. For example, someone could prompt a model with a specific piece of personal information and see if it generates something related to that person's private life.
That sounds like a real privacy nightmare.
It is, and researchers are working on techniques to mitigate these risks. One approach is differential privacy, where you add noise to the training data to make it harder to extract individual information. Another is federated learning, where you train the model across multiple devices without centralizing the data.
So, ways to protect the privacy of the data used to train these models.
Exactly. And there are also legal considerations. The paper mentions the lawsuit between the New York Times and OpenAI, which highlights the complexities of copyright when training these models on copyrighted material.
Right. It's a whole legal minefield.
It is. And there's also the issue of unlearning. If we find that the model has memorized some sensitive information, we need a way to remove that information from the model without retraining it from scratch. There are techniques for doing this, but they're still under development.
It's like trying to erase a specific memory from the model's brain.
Yeah, that's a good analogy. It's a really challenging problem, but it's essential for ensuring the responsible use of these models.
Absolutely. Another aspect of trustworthiness is interpretability. Why is it so important to understand how these models are making their decisions?
Well, with traditional machine learning models, we often have a good understanding of how the model is making its predictions. We can look at the features it's using, the weights it's assigning to different features, and so on. But with LLMs, it's much harder to understand what's going on inside the black box. They have billions of parameters, and the relationships between those parameters and the model's outputs are incredibly complex.
So it's hard to know what's driving the model's behavior.
Exactly. And this can be problematic for a few reasons. First, if we don't understand how the model's making its decisions, it's hard to trust those decisions. Second, if the model makes a mistake, it's hard to debug it or figure out why it made that mistake. And third, if the model exhibits some kind of bias, it's hard to identify and correct that bias.
It's like trying to understand the thought process of a superintelligent alien.
Yeah, it can feel like that sometimes, and there's a lot of research going on into making these models more interpretable. Techniques like attention visualization, where you can see which parts of the input the model is focusing on, are helping us gain some insights.
It's like peering into the model's mind.
In a way, yes. And there are other approaches as well, like developing models with built-in interpretability or trying to reverse engineer the model's decision-making process. It's a very challenging area, but it's crucial for building trust in these systems.
Absolutely. Now, another major concern is fairness. These models are trained on data that reflects the biases present in society, and there's a risk that they could perpetuate or even amplify those biases.
Right. If the training data contains examples of, say, gender stereotypes, the model might learn to generate text that reinforces those stereotypes, and this could have real-world consequences leading to discrimination.